Imagine, for a moment, a world where the horizon does not promise the gentle gradient of a sunset, but instead glows with a perpetual, hellish twilight, where the sky is not a vault of blue or a tapestry of stars, but a suffocating, inverted ocean of indigo and violet, pressing down upon a landscape of eternal dusk. This is not a landscape born of fantasy, but a planet catalogued by the unflinching gaze of orbital telescopes. A world designated HD 189733b, orbiting a star 65 light-years away in the faint constellation of Vulpecula, the Fox. It is a place of profound and elegant violence, where the atmosphere itself has turned against the very concept of solid ground, where the winds scream at speeds that would vaporize sound, and where the rain does not fall as water, but as a tempest of molten glass. Sideways. To understand this world, to truly comprehend the physics that forges such a phenomenon, we must first quiet our terrestrial instincts, and step slowly into the realm of the hot Jupiter, a class of planets so alien they defy the foundational architecture of our own solar system. Our journey begins not on the planet's surface, for there is likely no surface to speak of in any familiar sense, but in the silent, data-rich confines of an observation chamber, where the light of a distant star is parsed into a story. The story of HD 189733b was first written in the subtle, rhythmic dimming of its parent star, a dip in stellar brightness of just over 2%, repeating with clockwork precision every two Earth days. This was the telltale signature of a transit, the silent eclipse caused by a planet passing across the face of its star from our vantage point in the cosmic dark. But this simple measurement, this celestial heartbeat, was merely the opening sentence. The true character of the world began to bleed through in the spectrum, the decomposed rainbow of starlight. As the planet transited, a fraction of the star's light filtered through the planet's atmosphere, and in that filtered light, embedded like a faint chemical fingerprint, scientists found the signature of sodium, of water vapor, and of silicate particles. It was this last component, the silicate signature, that whispered the first hint of the storm to come. Silicates are the building blocks of rock, the minerals that form the bulk of terrestrial planets and the dust of cosmic clouds. On Earth, under the gentle pressure of our atmosphere and the benign temperatures of our crust, silicates cool into solid grains of sand, into the structure of quartz and feldspar. But physics operates on a sliding scale, and the rules change with the application of energy. On HD 189733b, the scale has been tipped into an extreme so far removed from our experience it becomes a form of abstract art. The planet lives an existence of profound intimacy and violence with its star, orbiting at a distance of just 3 million miles, a mere 1/30th of the space between Earth and our Sun. This proximity locks the planet in a gravitational embrace so tight it is likely tidally locked, one hemisphere forever facing the incandescent glare of its orange dwarf sun, the other turned eternally to the frozen blackness of interstellar space. This eternal day and eternal night create a thermodynamic engine of staggering power. The day side, seared by constant radiation, heats to temperatures exceeding 1,700 degrees Fahrenheit, hot enough to melt aluminum, to soften iron, and crucially, to vaporize rock. Here, on the bleeding edge of perpetual sunlight, the very bedrock of the planet is not solid. It is a component of the atmosphere. The silicate minerals are pulled from whatever passes for ground, perhaps a molten magma ocean or a supercritical fluid layer, and enter the gaseous state, becoming a mist of rock vapor, a fog of elemental doom hanging in a scorching sky. This is the raw material of the glass rain, not yet condensed, not yet given form, but suspended in a superheated, turbulent atmosphere that is in constant, frantic motion. For the thermodynamic engine does not allow for stagnation. The immense temperature difference between the day hemisphere and the night hemisphere, a gradient of thousands of degrees over a distance not much greater than the planet's own circumference, drives winds of unimaginable ferocity. Computer simulations and the subtle Doppler shifts in spectral lines tell a story of atmospheric currents moving not at hundreds, but at thousands of miles per hour, supersonic jets of gas that circumnavigate the planet in a relentless attempt to equalize the impossible, to ferry heat from the furnace of day into the abyss of night. And it is within this frantic, supersonic flow that the vaporized silicates begin their transformation. As the winds scream from the dayside into the twilight regions, the terminator line where day meets night, temperatures begin to plummet. There is no gentle cooling here, no gradual descent into evening. It is a violent thermodynamic shock. In this region of rapid cooling, the rock vapor can no longer remain gaseous. It must condense. And it does so not into delicate snowflakes or droplets of water, but into microscopic seeds of liquid rock, droplets of molten silicate. These droplets, born in the turbulent shear between atmospheric layers, are then caught in the very winds that forged them, whipped sideways across the sky in a blistering, horizontal downpour. They do not fall gently. They are fired like countless microscopic bullets, a scorching, abrasive hail that moves at speeds capable of stripping a spacecraft to its skeleton in seconds. As these droplets are carried further into the darkness, they cool further, hardening from liquid rock into solid glass spherules, a blizzard of sharp, tiny beads continuing their endless, wind-driven journey. Some models suggest these glass particles may eventually be swept back into the dayside by the planet's global circulation, where the furnace heat re-vaporizes them, closing a terrible and beautiful cycle of creation and destruction, a lithic water cycle of apocalyptic proportions. This is the reign of HD 189733b, a rain that never touches a surface in the way we understand, a rain that is a permanent feature of the sky, a constituent of the very air, if one can call it air. It is an atmosphere that is also a geology, a weather system that is also a rock cycle, all operating at a scale and intensity that renders our most violent terrestrial storms a silent, still photograph by comparison. To observe this world is to watch a fundamental alchemy of planetary science, where the categories of gas, liquid, and solid blur under extreme conditions, where the sky itself becomes a fluid forge, and where the precipitation is not a gift to the ground, but a permanent, swirling constituent of a global maelstrom. The detection of this phenomenon stands as a testament to a new era of astronomy, where we are no longer merely discovering planets, but are beginning, slowly and with immense effort, to read their weather reports, to decode the complex atmospheric chemistry of worlds we will never physically visit, and in doing so, to understand the breathtaking diversity of physical states that matter can assume under the guiding hand of gravity, radiation, and orbital mechanics. The glass rain is not an anomaly. It is a logical outcome, a prediction of physics played out on a canvas of extreme conditions. It tells us that the universe is capable of crafting environments of both sublime beauty and profound violence, often intertwined, and that the familiar processes we see on Earth, evaporation, condensation, precipitation, are universal verbs, even if the nouns they act upon are utterly alien. The process by which we came to know this world, to move from a mere blip in a light curve to a detailed, almost visceral understanding of its atmospheric fury, is a story of patient, incremental revelation, a kind of forensic astronomy conducted across an interstellar gulf. The Hubble Space Telescope, that venerable eye in the dark, played a pivotal role. Its Space Telescope Imaging Spectrograph, STIS, and later its Cosmic Origin Spectrograph, COS, acting as cosmic chemists, isolating the faint spectral signatures imprinted on the starlight during transit. But it was the Spitzer Space Telescope, sensitive to the infrared, the domain of heat, that truly pierced the veil. Spitzer observed HD 189733b not only as it passed in front of its star, but also as it vanished behind it, an event known as a secondary eclipse. This disappearance and reappearance allowed astronomers to perform a remarkable trick of celestial subtraction. by measuring the total light from the star and planet together just before the planet slipped behind the star, and then measuring the star's light alone while the planet was occulted, they could isolate the faint infrared glow emanating from the planet itself. This glow is not reflected starlight, but thermal radiation, the planet's own heat bleeding into space. Mapping this heat revealed the first direct evidence of the planet's fierce winds. The hottest point on the planet was not, as one might naively expect, at the substellar point directly under the star, but was offset by thousands of miles, dragged downstream by the supersonic atmospheric currents. It was as if the peak temperature of a forest fire was being carried kilometers downwind by a hurricane, a vivid testament to the planet's relentless atmospheric redistribution of energy. Furthermore, by observing the planet at different wavelengths in the infrared, Spitzer could, in effect, take the planet's temperature at different altitudes within its atmosphere, constructing a crude but revolutionary vertical profile. It was data like this that provided the context for the silicate signature. The temperatures inferred were more than sufficient for silicate vapors to exist, and the physics of condensation dictated what would happen as those vapors were swept to cooler climes. This is where the narrative of HD 189733b transcends mere observation and enters the realm of sophisticated simulation, of computational fluid dynamics operating on a planetary scale. Scientists, using supercomputers to model the atmospheric circulation of these hot Jupiters, had long predicted the possibility of such exotic condensation cycles. These models are not mere animations. They are complex implementations of the Navier-Stokes equations of fluid motion, coupled with radiative transfer codes and detailed chemical equilibrium calculations, all straining to approximate the chaotic, three-dimensional reality of a planetary atmosphere under extreme forcing. The models suggested that on the hottest of these worlds, where dayside temperatures soar above the vaporization points of common minerals, the atmosphere would become enriched with metallic vapors and silicate clouds. The condensation of these clouds would not occur in fluffy, vertical structures like terrestrial cumulus, but in thin, stratified layers and sheets, driven horizontally by the jet streams. For HD 189733b, the match between the observed spectroscopic data, the hint of silicate absorption, and the model predictions of silicate cloud formation in a rapidly moving, temperature-stratified atmosphere was a profound moment of validation. It meant we were not just seeing a chemical component. We were beginning to see the dynamic weather system that organized that component into a global phenomenon. This world, therefore, exists at a precise and cruel equilibrium of forces. Its gravity, roughly similar to Jupiter's but compressed into a slightly larger package due to intense heating and internal pressure, is strong enough to hold onto an atmosphere of hydrogen and helium that has been bloated and puffed up by the stellar radiation. Yet that same radiation provides the monumental energy input that drives the atmospheric engine. The tidal locking ensures a permanent, stark temperature dichotomy, the piston for that engine, and the planet's composition, born from the same protoplanetary disk as its star, provides the raw silicate material. Alter any one of these parameters, a slightly wider orbit, a slightly less massive star, a different bulk composition, and the glass rain might not form. It might instead be a rain of molten iron, as hypothesized on the even hotter WASP-76b, or a snow of titanium oxide, or perhaps no mineral precipitation at all. This contextualizes HD 189733b not as a singular freak, but as a data point in a vast spectrum of planetary possibilities, a particularly vivid example of a phase space where atmospheric physics and mineralogy violently merge. The glass rain also forces us to reconsider the very meaning of a surface. For a gas giant like Jupiter or Saturn in our own system, we speak of a surface as a conceptual boundary, the depth at which the pressure is so great that hydrogen becomes metallic, a gradual transition from gas to fluid. For HD 189733b, the idea is further complicated. The extreme heat at the day side may prevent the formation of any traditional, distinct cloud deck or liquid ocean layer. Instead, the atmosphere may extend downward in an increasingly dense, hot soup, with silicates and other minerals remaining in vapor formed to great depths, eventually reaching a supercritical fluid state where the distinction between gas and liquid vanishes entirely. The ground, if it exists, might be a realm of physics so exotic that our terrestrial terminology fails. The rain, then, does not fall to a surface, but exists within an atmospheric column that itself constitutes the planet's outer identity. It is a permanent suspension, a storm without end or beginning, a constituent of the planet's being. This leads us to a deeper, more philosophical implication of such a discovery: the challenge of imagining, of truly conceptualizing, an environment that operates under such alien rules. Our brains are exquisitely tuned to the physics of Earth, the gentle fall of water droplets at terminal velocity, the soft accumulation of snow, the way wind rustles leaves. To comprehend a horizontal blizzard of molten glass moving at 7 times the speed of sound requires a conscious setting aside of intuition, an embrace of the sheer, scalable power of natural law. It is a demonstration that the universe is under no obligation to be comprehensible to our senses, yet through the rigorous application of mathematics and indirect observation, it becomes so. The glass rain of HD 189733b is, in this light, a masterpiece of natural engineering, a system that is both terrifying and perfectly coherent, a logical outcome written in the laws of thermodynamics and fluid dynamics, played out with stellar energy capital on a planetary stage. It whispers that the cosmos is replete with such masterpieces, each waiting for its light to be parsed, its story to be slowly, patiently decoded from the faint whispers carried across the light years. If the atmosphere of HD 189733b is a fluid forge, then the question of what lies beneath its perpetual storm beckons with a deeper, more profound mystery. Our understanding of planetary interiors is, even for Earth, an exercise in indirect inference, relying on seismic waves and gravitational fields. For a world 65 light-years distant, the task is magnitudes more subtle, a grand exercise in theoretical extrapolation from a handful of data points: the planet's mass, its radius, its bulk density, and the extreme external conditions imposed upon it. The mass and radius tell us that HD 189733b is a classic, hot Jupiter, with a mass about 13% greater than that of Jupiter, but a radius approximately 12% larger. This inflation is a crucial clue to its inner workings. Pervasively heated from above by its nearby star, the outer atmospheric layers are swollen, less dense than they would be in isolation. But this external puffing is just the outermost symptom of a complex internal energy budget. The interior of such a planet is a realm of staggering pressures and temperatures even without stellar irradiation, a place where hydrogen, the primary constituent, undergoes a phase transition from a molecular gas to a metallic liquid, a state of matter that does not exist naturally anywhere on Earth. This metallic hydrogen layer, electrically conductive and dynamically churning, is thought to be the engine that generates the powerful magnetic fields of Jupiter and Saturn. For HD 189733b, the presence of a magnetic field is more than an academic curiosity. It is a potential architect of its outer atmospheric character, while direct measurement of its magnetosphere remains beyond our current reach. Theoretical models suggest that the intense stellar wind and radiation pressure from the nearby star would compress any planetary magnetic field into a tight, magnetospheric cavity, potentially interacting with the upper atmospheric layers in ways that could enhance atmospheric loss over astronomical timescales. This stellar wind, a relentless stream of charged particles, batters the planet's dayside, potentially shearing away atmospheric material. Though the planet's substantial gravity works tirelessly to hold on, This interplay, stellar erosion versus gravitational retention, may sculpt the long-term evolution of the planet's atmosphere, perhaps slowly stripping away the lighter elements over billions of years, leaving behind a denser, more enriched envelope. The internal heat of the planet itself is another critical variable. Gas giants are not cold from formation. They retain a substantial reservoir of primordial heat from their gravitational collapse, and in some cases, additional heat from the ongoing differentiation of heavier elements sinking towards the core. This internal heat flux, rising from the deep interior, must navigate its way through the stratified layers of metallic and molecular hydrogen, eventually meeting the downward cascade of stellar energy from the atmosphere above. The convergence of these two heat flows, one from the planet's fiery birth, the other from its stellar imprisonment, creates a complex thermal structure that dictates everything from the depth of the atmospheric weather layer to the very possibility of a distinct core. Which brings us to the heart of the matter, both figuratively and literally. Does HD 189733b possess a core? In the traditional core accretion model of giant planet formation, a solid core of rock and ice first forms, growing until it is massive enough to rapidly accrete a vast envelope of hydrogen and helium from the protoplanetary disk. If this model holds, then somewhere deep within the swirling metallic hydrogen, under pressures of millions of atmospheres, there may reside a compact, extraordinarily dense nugget of elements like iron, silicon, magnesium, and oxygen, the very stuff that, vaporized and lofted high above, now forms the glass rain. This core would be a phantom limb of the planet's formation, a relic buried under the overwhelming bulk of its gaseous acquisition. However, alternative formation scenarios, such as disk instability, where a giant planet collapses directly from a dense knot in the protoplanetary disk, might not necessitate a substantial solid core at all. The composition of the silicate vapor in the atmosphere suggests these heavy elements are present and accessible, but whether they are concentrated in a central core or more uniformly mixed throughout the deep interior remains an open question, one that speaks to the very origin story of this world and countless others like it. The extreme external heat may also have profound implications for the internal structure. On a Jupiter orbiting peacefully in the cold of our outer solar system, the different layers, the gaseous outer envelope, the liquid molecular hydrogen layer, the metallic hydrogen layer, and the potential core, are relatively stable and distinct. But on HD 189733b, the immense and constant influx of stellar energy from above could blur these boundaries. The heat may penetrate deeply, preventing the formation of a sharp transition to metallic hydrogen, or causing a more gradual, diffuse change in state. It could keep the deeper layers in a state of more violent convection, stirring the pot of the planet's interior with a ferocity unknown in our solar system's giants. This constant stirring might even act to homogenize the interior, preventing heavy elements from fully settling into a centralized core, instead maintaining a dilute, or mixed, interior where silicates and other metals are dissolved or suspended throughout the vast hydrogen-helium envelope. In this scenario, the glass rain would not be sourced from a distant, detached surface, but would be the atmospheric expression of a planet that is, in its very essence, a homogeneous mixture of rock and gas, a chthonic broth brought to a boil by its star. The intense pressure and temperature at depth might create conditions where these silicates exist not as solid rock or simple vapor, but in exotic, high-pressure phases or as components of a supercritical fluid that defies simple classification. The journey of a silicon atom, then, could be a grand, cyclical odyssey. Perhaps it spends eons dissolved in the metallic hydrogen sea, is gradually lifted by deep convection into the molecular envelope, where decreasing pressure allows it to form silicate vapor, which then rises into the raging weather layer to condense into glass, only to be eventually subducted back into the depths by atmospheric circulation or the slow, gravitational settling of the heavier droplets. This would make the glass rain not merely an atmospheric phenomenon, but a surface manifestation of the planet's entire internal geochemical cycle, a window into the otherwise hidden circulatory system of a giant world. Contemplating this depth, this layered complexity, transforms HD 189,733b from a two-dimensional image of a storm-racked orb into a three-dimensional, dynamic entity with a deep history and an active, seething present. It is a world with a hidden heart, whose internal rhythms, born of its formation and sustained by its stellar bondage, ultimately pulse into the furious atmospheric ballet we observe from our distant, quiet vantage point. The supersonic winds, the sideways glass rain, the indigo twilight, these are merely the outermost whispers of a vast, integrated system, a single line of poetry in a much longer epic of planetary evolution. To understand the rain, we must therefore listen for the echoes from the deep, for the subtle gravitational tugs or the faint thermal signatures that might, in some future era of even more sensitive observation, hint at the churn of metals in the abyss below. For now, that interior remains a realm of elegant theory, a dark canvas upon which we project our understanding of physics at extremes, knowing that the truth is likely stranger, more intricate, and more beautifully convoluted than our best models can yet dream. The narrative of HD 189,733b, while compelling in its own right, gains even greater resonance when placed within the broader cosmic context of planetary diversity, serving as a critical reference point in a taxonomy of atmospheric extremity. It is not alone in its infernal precipitation. It is part of an emerging class of worlds where the very concept of weather is rewritten in the language of high-temperature chemistry and supersonic fluid dynamics. Consider, for a moment, its more extreme cousin, WASP 76b, a hot Jupiter orbiting so close to its F-type star that its dayside temperatures soar above 4,400 degrees Fahrenheit, hot enough to vaporize iron. Here, the thermodynamic engine operates with even greater violence. Models and tentative observations suggest that on this world, iron is lifted as vapor from the scorching dayside, swept aloft by hypervelocity winds, and condenses into droplets as it crosses into the nightside. The result is hypothesized to be a rain of molten iron, a dramatic metallic drizzle falling through a twilight sky. The atmospheric dynamics of these two worlds, while similar in principle, are tuned by their respective stellar inputs and orbital parameters, producing different condensates, silicate glass versus iron, like different outputs from a universal atmospheric forge. On the cooler, but still intensely hot, HAT P7b, studies of its reflected light hinted at the possible presence of clouds composed of corundum, the mineral family that includes sapphires and rubies. One could imagine, though not yet confirmed, a scenario where the condensation of such minerals leads to a precipitation of gemstone crystals, a glittering, abrasive snow driven by winds of unimaginable force. These are not mere fantasies. They are predictions grounded in chemical equilibrium calculations. Given a bulk elemental composition similar to that of a rocky planet but enveloped in a vast hydrogen-helium atmosphere and placed at a specific temperature and pressure regime, certain compounds will vaporize, and others will condense. The atmosphere becomes a vast, continuous distillation column, sorting elements and compounds by their volatility, their condensation temperatures, and the dynamics of the global wind flow. This perspective allows us to see HD 189,733b not as a singular oddity, but as a benchmark. Its equilibrium temperature, while extreme, sits at a pivotal point where silicates, common throughout the galaxy, transition between solid, liquid, and vapor. It is a Rosetta Stone for interpreting the atmospheres of other highly irradiated worlds, a template against which we can compare spectroscopic signatures from other exoplanets and ask, do we see evidence of silicate clouds here? Is the thermal phase curve offset, indicating fierce winds? The answers help us map the complex phase space of exoplanetary atmospheres. but the implications spiral outward even further, touching upon one of the most profound quests in modern astronomy, the search for habitable worlds. The study of these hellish, uninhabitable planets is, paradoxically, essential to that search. They are our laboratories for understanding atmospheric physics and chemistry under extreme forcing, for testing and refining the computer models that we must later rely upon to interpret the subtler, more ambiguous signals from smaller, cooler, potentially rocky worlds in the habitable zones of their stars. If we cannot accurately model the atmospheric circulation and cloud formation on a hot Jupiter, where the signals are strong and the physics pushed to a dramatic extreme, our confidence in modeling the more temperate, complex atmosphere of an Earth-like exoplanet would be unjustified. The techniques pioneered to detect sodium, water, and silicates in the hazy, bloated atmospheres of hot Jupiters, transmission spectroscopy, emission spectroscopy, phase curve analysis, are the very same techniques being painstakingly refined for use on terrestrial targets by the James Webb Space Telescope and future observatories. HD 189733b, in all its violent glory, was a training ground, a cosmic wind tunnel where our methods were stress-tested against a known, if alien, environment. Furthermore, the existence of such worlds challenges our definitions and broadens our imagination of what a planet can be. Our solar system presented us with a neat dichotomy: small, rocky inner worlds and large, gaseous outer giants, with a clear frost line separating their formation histories. The discovery of hot Jupiters, orbiting blisteringly close to their stars, shattered that simple schema. It revealed that planetary migration is a powerful and common force, that systems can be dynamically scrambled, and that a planet's present location is not necessarily a reliable record of its birthplace. HD 189733b almost certainly did not form in its current infernal proximity to its star. It likely formed further out in the cooler reaches of its protoplanetary disk, where ice and rock could coalesce into a core, and then spiraled inward through interactions with the disk or with other planets. This migration history may have left its own imprint, perhaps stirring its interior, altering its spin, or even stripping away an earlier, more extended atmosphere. Its current state is therefore a palimpsest, a present condition written over a past of dramatic movement and transformation. This narrative of migration and atmospheric persistence also touches on the delicate question of atmospheric survival. Can a gas giant withstand billions of years of such proximity to a star? The relentless stellar wind and intense ultraviolet radiation create a plasma environment around the planet that may continuously erode its outer layers, creating a comet-like tail of stripped gas. Some theoretical studies suggest that over the lifetime of a star, a hot Jupiter could lose a significant fraction of its mass through this photoevaporation. This raises the possibility that what we see today as a puffy, bloated gas giant might, in some cases, be the stripped-down remnant of an even larger planet, or perhaps the exposed core of a former giant, a so-called Chthonian planet. While HD 189733b, with its strong gravity, is likely resilient against total stripping, the process may be shaping its atmospheric composition and density. Every observation we make is thus a snapshot in an eons-long process of stellar weathering. The planet endures, but it is not static. It is in a constant state of dynamic equilibrium, its atmosphere boiling off into space even as its gravity tenaciously holds on, its interior churning, its winds screaming, its glass rain perpetually falling in a cycle that may be as ancient as the planet itself, yet as ephemeral, in a cosmic sense, as a single droplet condensing in a storm that has raged for 1 billion years. To observe it is to witness a moment in this grand, slow-motion drama, a drama written in the fundamental laws that govern all matter, but staged with a ferocity that exists only in the most extreme corners of star systems far removed from our own tranquil celestial neighborhood. As we extend our gaze from the specific, tumultuous reality of HD 189,733b towards the broader philosophical and scientific horizons it unveils, we find ourselves standing at a precipice of understanding, where the concrete data of observation melds with the profound implications for our place in the cosmos. This world of glass rain serves as a powerful corrective to a latent, terrestrial parochialism, a silent reminder that the processes we consider universal, rain, wind, the cycle of evaporation and condensation, are not bound to the specific chemistry of water or the temperate pressures of Earth. They are universal principles, templates of phase transition and energy transfer that will manifest wherever an atmosphere and an energy gradient coexist, regardless of the substances involved. This realization is both humbling and exhilarating. It expands the canvas of planetary science from a study of the few examples in our solar system to a truly universal discipline, where the periodic table becomes a palette and orbital dynamics the brush, painting environments of staggering variety. The quiet, persistent detection of these worlds, pixel by pixel, spectrum by spectrum, is a form of cosmic cartography, mapping not just locations in space, but territories in a landscape of physical possibility. In this expanded view, HD 189,733b is a sovereign nation in an empire of extremes, with its own laws of weather, its own geology of the sky, its own version of a water cycle written in silicon and oxygen. This forces a fundamental shift in perspective. When we search for life, or even simply for familiar conditions, we must consciously avoid the trap of assuming that Earth's particular solutions are the only ones of significance. The universe is under no obligation to cater to our biochemistry. It operates on a vaster, more neutral principle of allowing all physically permissible states to exist. The glass rain is a majestic, terrifying testament to that neutrality. It is not malevolent, it is indifferent, a perfectly natural outcome that happens to be utterly incompatible with life as we know it. This very incompatibility, however, is what makes it so scientifically precious. It is a clean laboratory, a system where the physics is so dominant, so overwhelming, that it strips away biological complexity and reveals the raw, elegant machinery of planetary systems in high-definition relief. Furthermore, the existence and characterization of such worlds deepens the mystery of our own solar system's apparent calm. Why do we have no hot Jupiter here? Was our disk structure different? Did Jupiter's formation and migration history, perhaps truncated or stabilized by Saturn, spare the inner rocky planets from being engulfed or ejected? The quiet orbits of Mercury, Venus, Earth, and Mars may be the result of a fortuitous, or at least non-catastrophic, dynamical history, a history that allowed for the prolonged, delicate experiment of life on at least one world. In contrast, the HD 189,733 system presents a narrative of violence and rearrangement, a story where a giant planet was pulled into a searing embrace with its star, a gravitational settling that would have utterly disrupted any nascent terrestrial planets in the inner system, scattering them or consuming them. Our search for Earth-like planets, therefore, may inherently be a search for solar systems that have avoided such dramatic dynamical upheavals, systems where giant planets either never formed close in or migrated inward early and violently before rocky planets had a chance to coalesce in stable orbits, or conversely, systems where giants remained peacefully in the outer darkness. The prevalence of hot Jupiters, while now understood to be less common than once thought, tells us that our peaceful arrangement is not the only possible outcome, and perhaps not even the most common. This imbues our own planetary neighborhood with a new sense of fragility and fortune. Looking forward, the legacy of HD 189,733b is securely woven into the fabric of future exploration. It stands as a benchmark, a standard candle, of sorts for atmospheric characterization. As the James Webb Space Telescope turns its golden eye towards other exoplanets, the data and models refined on this world will be the comparative baseline. When Webb detects a featureless transmission spectrum for a hazy world, HD 189,733b's clearer, albeit complex, spectrum will be the contrast. When phase curves of new planets are measured, the pronounced offset and amplitude seen in this world will serve as a textbook example of efficient heat redistribution and atmospheric dynamics. It has taught us what to look for, how to interpret the subtle whispers of molecules and aerosols in the light of a distant star. Beyond Webb, future telescopes like the Extremely Large Telescope and space-based direct imaging missions will attempt an even more daring feat, to spatially separate the faint glow of a planet from the blinding glare of its star. In those first, blurry images of exoplanets as actual pixels, not just inferred shadows, the atmospheric models trained on hot Jupiters will be crucial for interpreting what we see. A pixel that brightens and dims as the planet rotates could reveal cloud patterns, perhaps even the asymmetric flow of weather systems. The supersonic winds of HD 189,733b, inferred from phase curves, may one day be corroborated by tracking cloud features across the visible face of a similar world. Each new discovery will recursively deepen our understanding of this archetypal world itself. The final contemplation, as we sit in the silent aftermath of this exploration, is of time and impermanence. The glass rain falls now, as it likely has for hundreds of millions, perhaps billions, of years, but its star, HD 189,733, is a K-type dwarf, a star with a lifespan longer than that of our Sun. It will shine on, steadily, for tens of billions of years. The planet, locked in its embrace, will continue to endure its fury. Yet, even this seemingly eternal storm is transient on a cosmic scale. Stellar evolution is slow but inexorable. As the star ages, it will very gradually brighten and expand. The planet's atmosphere may be stripped away more vigorously, or its interior may be heated even further. In the very distant future, the star will eventually leave the main sequence, entering its red giant phase. What happens then is a matter of celestial mechanics and tidal forces. The expanding star may engulf the planet entirely, swallowing it in a final, fiery confluence, vaporizing not just the atmosphere but the very core, ending the cycle of glass rain forever. Or, if the planet's orbit has decayed sufficiently, it may be ripped apart by tidal forces before engulfment, its material adding a brief, metallic enrichment to the star's outer layers. In either scenario, the storm does not end with a whimper, but with a grand, stellar-scale dissolution. The atoms that once swirled in a horizontal blizzard of molten glass will be returned to the stellar furnace, perhaps to be incorporated into new planets, new systems, in some future cycle of cosmic birth. This is the ultimate lesson of HD 189,733b and worlds like it. They are not static postcards, but dynamic, evolving entities with birth, life, and death written in the slow, patient script of astrophysics. They show us that the universe is a place of both immense creative power and immense destructive force, often one and the same, and that within the vast, cold dark, there are pockets of furious, beautiful process, where matter is compelled to dance in forms of both exquisite and terrifying elegance. The silent, distant observation of a world where it rains molten glass is, therefore, an act of profound connection, a connection not of kinship, but of understanding, a bridge of knowledge across the light years that allows us to comprehend, in some small measure, the magnificent and indifferent artistry of physical law. The story of HD 189,733b, however, does not conclude with a passive observation of its fiery fate. It spirals back inward, challenging us to refine the very tools of our perception and to question the limits of our knowledge gleaned from such immense distances. For all the vivid detail we have painted, our understanding remains, by necessity, a masterpiece of inference, a sculpture carved from the sparse shadows and faint spectral colors cast by a world we will never directly touch. The silicate signature, the offset hotspot, The atmospheric models, they form a coherent, compelling narrative, but they are not the same as in situ measurement. The glass rain itself has never been imaged. It is a phenomenon deduced, a logical and beautiful conclusion drawn from a symphony of indirect evidence. This space between deduction and direct experience is where the true scientific drama quietly unfolds. It necessitates a careful, humble acknowledgement of the uncertainties that cling to our conclusions, like the tenuous haze we suspect hangs in that alien atmosphere. The precise size and composition of the silicate condensates, for instance, are not known. Are they microscopic spheres, perfect little beads of glass formed in a moment of rapid cooling? Or are they more irregular, jagged particles, aggregating and fragmenting in the turbulent winds? The details of the condensation process, whether it occurs homogeneously in the clear air or nucleates on pre-existing seed particles of other, more refractory materials, could alter the optical properties of the clouds and haze, which in turn affects how we interpret the spectroscopic data. Our models, for all their sophistication, are still simplifications of a staggeringly complex reality. They must parameterize turbulence, cloud microphysics, and chemical kinetics in ways that are computationally manageable but may miss subtle, yet important, nonlinear interactions. The atmosphere is treated in broad, global strokes, but it may harbor more intricate, small-scale structures, localized jet streaks, storm cells of condensing silicate, or waves propagating from the deep interior, that are currently below the resolution of our detection methods. Furthermore, the planet's atmospheric composition is not a static, uniform given. It may vary with altitude, with longitude, and even with time. Stellar activity, the ebb and flow of radiation and charged particles from the host star, could be constantly perturbing the upper atmosphere, driving photochemistry that creates new molecular species and alters the opacity at different wavelengths. A stellar flare, a common occurrence on K-type dwarfs, could blast the planet's day side with a surge of X-ray and ultraviolet radiation, momentarily heating the upper layers to even more extreme temperatures, potentially altering the condensation sequence or even temporarily boiling away the silicate clouds, only for them to reform as the flare subsides. The planet's weather, in other words, may not be a monotonous, eternal storm, but a system with its own climate variability on timescales of hours, days, or years, patterns we are only just beginning to have the observational baseline to potentially detect. This introduces a profound temporal dimension to our study. A single transit observation is a snapshot. Multiple transits over years can reveal changes in the transmission spectrum, hints of an evolving atmosphere. Monitoring the secondary eclipse depth at different epochs could show variations in the dayside temperature, a sign of changing cloud cover or circulation patterns. We are transitioning from studying exoplanet atmospheres as fixed snapshots to studying them as dynamic systems with histories, a transition that mirrors the evolution of terrestrial meteorology into climatology. For HD 189733b, this means the glass rain may not be a perfectly constant downpour. It may have seasons of intensity and relative calm, dictated by the subtle interplay of internal heat flow, stellar irradiation cycles, and the chaotic dynamics of the atmosphere itself. The very fact that we can entertain such questions is a testament to how far exoplanet science has come, but it also delineates the frontier. The next great leaps will come from instruments capable of higher spectral resolution, which can disentangle overlapping molecular bands and probe atmospheric structure in finer detail, and from long, uninterrupted observational campaigns that can track atmospheric variability. The James Webb Space Telescope, with its exquisite infrared sensitivity and stability, is poised to contribute to this, potentially measuring the spectral signatures of different silicate compositions or even probing vertical temperature gradients with unprecedented precision. Yet, even Webb has its limits. The ultimate dream of directly imaging a planet like HD 189733b and resolving its atmosphere into a map, a globe of swirling indigo and violet, with bright and dark patches marking cloud formations, and the deep, hot glow of the day side remains for future generations of telescopes, perhaps those built on the moon or in space as giant, unfolding interferometers. When that day comes, the first such image will be compared, pixel by pixel, to the global circulation models that were pioneered and tested on this world. It will be a moment of profound validation or of equally profound disruption, forcing a re-evaluation of our assumptions. Until then, HD 189733b exists in a state of graceful suspension between data and dream, a known unknown that propels our curiosity forward. It serves as a permanent anchor in the sea of exoplanetary discovery, a fixed point whose detailed study raises more questions than it answers, which is the hallmark of a truly rich scientific subject. It asks us, what other condensation cycles await discovery? What happens on worlds with different chemical abundances, or on those caught in eccentric orbits that swing them between extreme heating and cooling? How do magnetic fields, if present, couple with these furious atmospheres? Each question branches into a new avenue of research, a new line of inquiry in the grand, slow-motion conversation between humanity and the cosmos. The planet, in its silent, stormy majesty, is both an endpoint of one journey of discovery and a luminous gateway to countless others, a reminder that every answer gleaned from the starlight is also a new question written in the dark. Beneath the turbulent narrative of atmospheric dynamics and the profound implications for planetary science, there exists a subtler, more intimate layer to the story of HD 189733b, a story of human ingenuity and the quiet, persistent labor that transforms starlight into knowledge. The planet's characterization is not the work of a single telescope or a eureka moment, but a cumulative tapestry woven from decades of technological advancement, theoretical foresight, and meticulous data analysis performed by countless individuals whose names are rarely spoken in the same breath as the wonders they reveal. It begins with the precise radial velocity surveys of the late 1990s and early 2000s, which first detected the gravitational wobble of the star, yielding the planet's mass and orbital period. It was then the fortuitous alignment of its orbit, allowing for transits to be observed from Earth, that opened the true window into its nature. The light curves from ground-based telescopes, painstakingly corrected for the twinkling distortions of our own atmosphere, provided the first clean measure of its radius and density. But the atmospheric revelations demanded space-based observatories, free from the contaminating glow of Earth's air. The Hubble Space Telescope, in its post-servicing mission life equipped with instruments like STIS and CUS, performed the delicate surgery of transmission spectroscopy, isolating the faint absorption signatures of sodium and water vapor. Each such detection was a victory wrested from a sea of noise, requiring the stacking of multiple transits to amplify a signal that was a fraction of a percent of the already minuscule dip in starlight. The Spitzer Space Telescope, operating in the thermal infrared, provided the complementary perspective of emission, mapping the heat distribution. The analysis of this data was itself an art form, involving complex algorithms to model and remove instrumental systematics, to disentangle the planet's signal from the star's own subtle variability, and to statistically validate that a faint dip in a light curve or a subtle shift in a spectrum was real, and not a phantom born of cosmic rays or electronic noise. The theorists, meanwhile, were building the conceptual framework to interpret these sparse data points. They drew from the deep well of planetary atmosphere science, built from studies of Jupiter, Saturn, and the brown dwarfs that straddle the line between planet and star. They adapted equations of state for hydrogen-helium mixtures at high temperatures, computed opacities for exotic molecules and aerosols, and ran massive fluid dynamics simulations on supercomputers that consumed millions of processor hours to simulate a single planetary rotation. The prediction of silicate clouds and supersonic winds predated the firmest evidence for them. The models said that if a planet had this temperature, this gravity, this composition, then such phenomena must occur. The observations then arrived, not to shock, but to confirm, tightening the bond between prediction and reality. This synergy is the quiet engine of modern astrophysics. The story of the glass rain is also a story of the evolution of a scientific community, learning to think in 3 dimensions about worlds seen only as one-dimensional lines in a graph. It fostered collaborations between astronomers, climatologists, chemists, and fluid dynamicists, creating a new interdisciplinary language. Early interpretations of exoplanet spectra were often simple, assuming clear, cloud-free atmospheres in chemical equilibrium. The data from HD 189733b and others forced a complication of that picture. The features were muted, the spectra often flatter than expected. This led to the realization of the ubiquity of hazes and clouds, even on these intensely hot worlds, a realization that demanded new modeling approaches and a deeper understanding of aerosol formation and microphysics. In this sense, the planet acted as a teacher, its data a corrective to overly simplistic assumptions, pushing the entire field toward greater sophistication and humility. Furthermore, the public narrative of this world, the headlines about a planet with glass rain, while a simplification, serves a vital purpose. It is a bridge between the abstruse mathematics of radiative transfer and the human capacity for wonder. That single, evocative image, horizontal rain of molten glass, translates gigabytes of processed data into a concept the imagination can grasp and marvel at. It makes tangible the incredible diversity of the cosmos, inspiring new generations to look up and ask questions. This cultural resonance is not an ancillary byproduct. It is part of the scientific ecosystem, fostering the public support that enables the funding and building of the next great telescope, the next instrument capable of probing even deeper. Yet, for all this, a poignant distance remains. We can describe the physics, run the simulations, and marvel at the imagery, but we cannot truly experience HD 189733b. This is the fundamental condition of interstellar exploration in our age. We are cartographers of the unseen, composing meticulous maps of territories we are sentenced only to observe from an unbridgeable shore. The scream of its winds, the feel of its heat, the visual spectacle of its indigo sky streaked with the glowing trajectories of countless molten droplets. These are forever beyond our senses, existing only in the realm of calculated simulation and informed imagination. This gulf, however, is not a void of ignorance, but a space filled with the substance of knowledge. We may never feel its storm, but we understand the forces that drive it. We may never see its glassy precipitation, but we know the chemical and thermodynamic principles that mandate its formation. This transformation of the unknown into the understood, even if not the experienced, is the profound gift of science. It allows us to hold the whole world in our mind, to comprehend its nature and its place in the cosmos, without ever leaving our own fragile, blue marble. In this act of remote comprehension, we perform a kind of intellectual ascension, elevating our perspective from a single point in space and time to a more cosmic viewpoint, from which even the most violent and alien of worlds can be seen as natural, explicable, and part of a grand, interconnected tapestry of physical law. HD 189733b, therefore, endures not merely as a catalog entry or a destination for telescopic observation, but as a permanent landmark in the expanding geography of the human mind. It is a place we have visited with our intellect, a storm we have charted with our equations, a world that has, in its own silent way, changed our understanding of what is possible under the suns of distant stars. As we circle back to the beginning, to the initial detection of a rhythmic dimming in the light of a star in Vulpecula, the journey of understanding HD 189733b reveals itself as a microcosm of the scientific endeavor itself, a slow, iterative convergence on a truth that is always more complex, more dynamic, and more strangely beautiful than first assumed. the planet has become a touchstone, a familiar stranger whose very name now conjures a specific and vivid set of physical ideas. Yet, even as we solidify our understanding, new theoretical frontiers emerge from its study, pointing toward deeper mysteries that lie entangled within its furious atmosphere and hidden interior. One such frontier is the question of atmospheric escape and its long-term geochemical consequences. The relentless stellar wind and high ultraviolet flux do not merely sculpt the outer atmosphere, they may be driving a continuous, hydrodynamic outflow of gas, primarily hydrogen, from the planet's dayside. This process, photoevaporation, acts as a selective filter. Lighter hydrogen escapes more readily, potentially enriching the relative abundance of heavier elements like oxygen, silicon, and magnesium in the remaining atmosphere over geologic time. This slow distillation could alter the very chemistry of the glass rain itself, perhaps making the condensates richer in certain refractory oxides, or changing the optical properties of the high-altitude haze. Furthermore, the escaping hydrogen gas, streaming away from the planet, could drag along some of the heavier silicate particles or vapor, creating an extended, comet-like tail of rocky material that might be detectable through specialized transit observations in the ultraviolet or through scattered light. The planet, in this view, is not a closed system, it is leaking its essence into space, contributing a faint metallicity to the interstellar environment of its star, a slow exhalation that accompanies the internal churn. Another frontier lies in the coupling between the deep interior and the atmospheric phenomena we observe. The internal heat flux, a relic of formation and potentially supplemented by tidal heating or the settling of heavy elements, must eventually be transported through the atmosphere and radiated into space. The efficiency of this transport depends on the atmospheric dynamics and opacity. The silicate clouds themselves play a critical role here. They are not passive passengers but active players in the energy budget. They can reflect incoming stellar radiation back into space, cooling the upper atmosphere, while simultaneously trapping outgoing thermal radiation from below, providing a greenhouse effect. The balance between these two opposing effects, albedo versus opacity, helps set the equilibrium temperature structure of the atmosphere, the distribution and particle size of the glass droplets, which are determined by the intricate microphysics of nucleation and growth in a supersonic flow, thus become key variables in the planet's global climate. This creates a feedback loop. The winds determine where clouds form, the clouds influence the temperature distribution, and the temperature gradients drive the winds. Understanding this coupled system in detail requires moving beyond static, one-dimensional models and into time-dependent, three-dimensional simulations that include cloud formation and evolution as an interactive component of the fluid dynamics, a computational challenge of the highest order. Moreover, the extreme conditions may foster chemical pathways that are negligible on cooler worlds. The high temperatures in the dayside atmosphere could promote the gas phase formation of unusual molecules or the thermal dissociation of more common ones. For instance, water vapor, readily detected, might be partially broken apart into atomic hydrogen and hydroxyl radical on the dayside, only to recombine as the gas flows into cooler regions. The silicate vapor itself might not simply condense as pure silicon oxide glass. It could interact with other atmospheric constituents like sodium or potassium to form more complex silicate species, or even metallic silicates, that condense at different temperatures, leading to a stratified sequence of cloud decks. The atmosphere could be a layered chemical refinery, with different compounds condensing out at different altitudes and longitudes, creating a complex, multi-hued shell around the planet. While our current spectroscopic tools may only see the broad silicate signature, future instruments with higher resolution and sensitivity might be able to discern the fingerprints of these more exotic compounds, adding another layer of richness to the atmospheric narrative. Finally, HD 189733b stands as a sentinel for a broader question about the demographics of close-in giant planets. What is the full range of their atmospheric states? By placing this world on a plot of equilibrium temperature versus atmospheric composition, we begin to map a phase diagram for hot gas giants. There will be worlds too hot for any condensates to form. With clear, vapor-dominated atmospheres, there will be worlds like HD 189733b in the silicate condensation zone, and there will be cooler worlds, perhaps with clouds of sulfides or chlorides, or even water clouds if they are sufficiently distant from their stars. Where exactly the transition zones lie, and how sharp or fuzzy they are, depends on a planet's specific chemistry, gravity, and irradiation history. Each new characterized exoplanet adds a point to this diagram, slowly filling in the boundaries between different atmospheric regimes. HD 189733b, as one of the first and best-studied members of its class, provides the anchor for the silicate cloud region. Its continued study, especially with the James Webb Space Telescope, will refine that anchor point, teaching us not just about one world, but about the physics that governs an entire category of planetary existence. In this ongoing exploration, the planet remains both a subject and a guide, its lessons illuminating the path forward into the ever-deepening mystery of exoplanetary diversity. A mystery that promises to reveal not only the outer workings of alien worlds, but also the fundamental principles that orchestrate the complex ballet of matter, energy, and motion under the watchful gaze of countless distant suns. The contemplation of such a world inevitably draws us beyond the confines of astrophysics and into a more reflective space, where the scientific narrative intersects with the deeper currents of human thought and our perennial quest to find meaning in the cosmos. HD 189733b, in its stark and violent elegance, becomes a mirror, reflecting not only the laws of physics but also the contours of our own understanding and the nature of our curiosity. It exists as a profound counterpoint to the cherished idea of cosmic hospitality, a living demonstration that the universe is not crafted for our comfort or even our comprehension, yet it remains comprehensively knowable through the language of mathematics and empirical observation. This duality, utter alienation coupled with intellectual accessibility, lies at the heart of the modern scientific worldview. We are creatures of a gentle world, evolved to perceive a narrow band of light, to withstand a slim range of pressures and temperatures, to thrive in a chemical milieu based on carbon and water. Our senses and intuitions are calibrated for this environment. A world of supersonic glass rain exists so far outside that calibrated range that it seems almost mythical, a fragment of some fevered cosmological dream. Yet, we have deduced its existence and described its mechanics with precision. This is a testament to the transcendent power of the scientific method, a tool that allows the human mind to escape the cave of its biological limitations and apprehend realities for which it has no innate reference. The planet, therefore, is a monument to reason, a validation that the cosmos, however strange, operates on consistent principles that can be uncovered through patient, collective inquiry. It enlarges our sense of the possible, not by offering a new home, but by demonstrating the breathtaking scope of natural architecture. In doing so, it quietly challenges any lingering anthropocentrism. For centuries, humanity placed itself at the center of creation, imagining the stars and planets as celestial adornments or divine omens. The Copernican revolution began the physical displacement, but the discovery of worlds like this completes a philosophical displacement. We are not the center. We are not the model. We are not even a particularly common template. We are a singular, perhaps rare, expression of planetary conditions, a delicate balance of factors that allowed for the persistence of liquid water and the complex chemistry of life. HD 189733b represents a vastly different expression, one where the balance tips toward ferocious extremes, where the very rock is sky and the weather is geology. It shows us that a planet can be a work of intense, dynamic art without any reference to biology whatsoever. Its beauty is a beauty of process, of pure physics manifest at a planetary scale, and in acknowledging that beauty, we expand our aesthetic sense to include the sublime terror of the impersonal universe. This expansion carries with it a certain solemnity. The study of such a world is, in a subtle way, an act of cosmic listening. We are attending to the story of another place, giving it the dignity of our attention, even though that story contains no characters like us and offers no possibility of visitation. It is a narrative of matter and energy, a chapter in the endless book of transformations that the universe writes for itself. By deciphering it, we perform an act of respect for the integrity of that other existence. We affirm that other worlds have their own truths, their own realities that are worthy of understanding for their own sake, not merely for what they can tell us about ourselves or our potential future. This shift from an instrumental view of the cosmos, what can it do for us, to an intrinsic one, what is it, is a mature step in our relationship with the universe. Finally, the enduring mystery of HD 189733b, the fact that our knowledge, however detailed, remains a web of inferences stretched across a gulf of space, preserves an essential sense of wonder. The unknown is not an emptiness to be filled and discarded. It is an ever-receding horizon that propels us forward. Each answered question about this planet's atmospheric circulation or cloud composition immediately suggests 3 more about its deep interior, its magnetic field, its long-term evolution under the fading glow of its star billions of years from now. The planet is a gift that keeps giving, not in the sense of providing resources, but in the sense of providing endless intellectual nourishment, a permanent catalyst for curiosity. It ensures that the act of looking up at the night sky remains charged with possibility, because we now know that around those faint points of light there whirl worlds of unimaginable variety, each with its own story waiting to be slowly, patiently translated from the faint language of photons into the rich narrative of science. In the grand, silent dialogue between humanity and the cosmos, HD 189733b has become an eloquent interlocutor, speaking not of life or companionship, but of the magnificent, indifferent, and endlessly creative power of physical law. A reminder that we are part of a universe capable of crafting both the fragile biosphere of Earth and the eternal, glass-laden storm of a world forever turning its heated face toward a distant, orange sun. And so, we arrive at the quiet culmination of this exploration, not with a definitive end, but with a sense of ongoing revelation, a recognition that the story of the planet with glass rain is woven into the larger, unfinished epic of human discovery. The light that left HD 189733 65 years ago, carrying within its photons the encoded story of sodium, water, and silicate vapors, has now been received, decoded, and contemplated. That light, now spent, has fulfilled its cosmic journey, but the intellectual journey it sparked continues to propagate, influencing the design of new instruments, the formulation of new theories, and the education of new minds. The planet itself, of course, continues its eternal rotation, unperturbed and unaware of the tiny, thinking beings in a distant spiral arm who have made it an object of such focused study. The supersonic winds still scream, the silicate vapor still rises from the dayside furnace, and the countless droplets of molten glass still condense in the twilight, swept sideways in a horizontal blizzard that will likely persist for eons to come. There is a profound serenity in this disconnect, the serene, detached violence of the world itself, existing in perfect accordance with natural law, and the quiet, persistent curiosity of the observers, striving to understand that law from a place of profound safety and distance. This relationship defines our current age of astronomy. We are witnesses to grandeur, not participants in it. Our role is not to conquer or colonize, but to comprehend and to marvel. In this, HD 189733b serves as a perfect teacher, for it offers no possibility of visitation, no promise of resources, no threat of invasion. It offers only knowledge, and in that offering, it is priceless. It has taught us about atmospheric dynamics under extreme irradiation, about the exotic phases of matter, about the universality of weather cycles, and about the subtle art of reading a planet's biography from the faintest of spectral lines. As we turn our collective gaze forward, the legacy of this world is already embedded in the ambitions of future missions, concepts for space-based interferometers, star shades flying in formation with telescopes, and giant ground-based extremely large telescopes all have, implicit in their design goals, the desire to do for other planets what has been done for HD 189733b, but with ever greater fidelity. The first direct spectrum of an Earth-like exoplanet, when it is finally obtained, will be analyzed using techniques and comparative data honed on this and other hot Jupiters. The models that will interpret the potential biosignatures in such a spectrum, the tricky disentangling of biological from geological and atmospheric signals, are being stress-tested against the complex, abiotic atmospheres of worlds like this one. Thus, the glass rain falls, in a very real sense, on the path to finding other pale blue dots. It clears the haze of our ignorance, offering a hard, clear lesson in planetary science that makes the subtle signatures of life elsewhere more discernible. In the final analysis, the significance of HD 189733b transcends its specific, terrifying meteorology. It represents a turning point in our cosmic self-awareness. We have moved from simply finding planets to beginning to know them as complex, individual worlds. We are no longer just counting. We are characterizing. We are learning their weather, their chemistry, their climates. Each such world, from the hottest ultra-hot Jupiter to the coolest super-Earth, adds a verse to a growing poem about the diversity of cosmic creation. This particular verse, written in silicon and oxygen, wind and fire, is one of the most vivid yet composed. It speaks of a universe that is not merely vast in space, but vast in possibility, capable of environments that stretch the very definitions of our language. As the stellar winds of HD 189733 continue to blow and its glass rain continues its endless, sideways fall, we here on our own world, under our own gentle sky, continue to watch, to learn, and to integrate these distant truths into our understanding of the whole. The planet endures as a silent beacon in the data streams of our observatories, a constant reminder that out there, beyond the familiar, the physics we know paints pictures we are only beginning to imagine. In a gallery of worlds whose number and variety promise to humble and inspire us for all the centuries to come.